Yesterday we began our new unit, magnetism, and we defined one important term. It was domain. A domain, if you remember, is a tiny little region, a tiny microscopic region inside this material that we call a ferromagnetic material that is represented by an arrow. Now, does anybody remember what a ferromagnetic material is? Because it's kind of important to know what that is in order that we know what a domain is. A ferromagnetic material is a material that can be good. It's a material that can be magnetized, like iron or steel or cobalt or some other materials that have that potential to become magnetized. So this ferromagnetic material has these tiny little domains inside it. They're not arrows. If you look at it in a microscope, you're not going to see these arrows, but it's represented by arrows. And these arrows in this ferromagnetic material are pointing in usually more or less random directions, unless there's some reason for them to not be pointing in random directions. When we align those domains, when we get them pointing in the same direction or at least similar directions, then we start noticing magnetic effects in there. Now, there's a couple of ways in which we can align these domains, a couple of ways in which we can get them pointing kind of, or to some degree at least, in the same direction. What's one of the ways that we can align them in the same direction? Yep. No, you can't put a current through the material. You could put a current through the material because generally we're talking about iron or steel or some kind of conductor, right? But putting a current through the material is not what we're going to do to magnetize it, but rather putting a current around the material. If we've got a wire here, that wire has an electric current going through it. It generates its own magnetic field, and we're going to learn more about that today, the whole idea of the current in the wire generating a magnetic field. But for now, just trust me. This current generates a magnetic field, and that magnetic field that the wire produces is going to magnetize this non-magnetized ferromagnetic materials. It's going to cause these domains to point at least more or less in the same direction. Now, it's temporary. It's a temporary magnet because as soon as we shut off that current, then those domains are going to go back to the way they were before, pointing in random directions. It's not necessarily going to be instant, but it's going to be relatively quick. Now, you guys have all seen on TV the big electromagnets they have at junkyards, right? They pick up a car and then they swing it over here and then they drop it. They apply a big electric current, a very strong electric current through the wire, produce a strong magnetic field, magnetize this piece of steel that the wire is wrapped around, pick up the car, okay, they pick up the car and then they haul it over here and then they just flip a switch, shut off the current, and the force of gravity takes over and the car drops wherever they want it to drop. That's one way to do it. What's the second way to magnetize this non-magnetized ferromagnetic material with domains pointing in random directions? What's the second way? The easier way. Louis? Yeah, doing a magnet next to it or some type of external magnetic field. Yesterday we drew it as bringing another magnet nearby it, but that other magnet could be the Earth, because it's got a magnetic field, right? It's a weak magnetic field. Okay, it's a very weak magnetic field, in fact, compared to even the bar magnets that you used in yesterday's activity. But it's still strong enough to eventually cause these domains to point more or less in the same direction. So they're going to start pointing like this. At least, kind of like that at least. Now, what's the polarity of this magnet that we just produced? Which end is the North Pole, which end is the South Pole? Yep. Good. North is on my right, the south is on the left. We define the direction of these domains as being from south to north. Now, after we talked about domains yesterday, we talked about magnetic fields. If we were to draw the magnetic field that surrounds this new magnet that we've just produced, this temporary magnet that we just produced, which way would the magnetic field go? If I was to draw the field lines around it, it's going to look something like this, right? Which way would they go? North to south. So it's going to leave the north end, go toward the south end. Notice that the field lines are really just extensions of the domains. If the domains, or you could even think of it inside the magnet as the magnetic field, the domains, the magnetic field inside the magnet point from south to north, then the magnetic field outside the magnet is really just a continuation of those domains or the magnetic field inside. And of course, that's going to go from north to south. What's the other way that we define the direction of magnetic field? First way is from north to south. Second way is the direction in which a a compass needle points. If you forget that, just think about the little activity we did yesterday, right? We stuck the compass in the magnetic field. We saw which way the compass points. We draw the little arrow showing the direction of that magnetic field. So A, the direction that the compass points when placed in the magnetic field, and B, you can define it as being away from the north and toward the south. Let's draw a couple more field lines, or a couple field lines around a couple more situations here. I'm going to do a little bit differently today. I'm going to draw some field lines, but I'm not going to tell you what the magnets are. What do you know about that situation right now based on the field lines that you see right there? Oops, this one's wrong though. What do you know about those two magnets based on those field lines? Tell me one thing you know about it, John. Good. They're like poles. How do you know that these two, at these two ends, are like poles, John? Good. The fields repel each other. What do we know about repelling fields or repelling magnets? Like poles repel each other. Okay? That's one of the laws of magnetism, right? Like poles repel each other. So if these fields are repelling each other, we know these have to be like poles. Do we know whether they're north or south? John? No, we don't know whether they're north or south. What do we got to know in order to determine whether they're north or south? Good, the direction of the magnetic field. I'm going to draw in one magnetic field line direction here, just one. Okay, it's going to go like this. There. Is that enough to tell me what the polarity is now? Yes, it is. Okay, what's the polarity of this one right here? It's going to be south because the magnetic field lines go from north to south. Now, if that's south, because the one magnetic field line is going that way, then we know the direction of the rest of the magnetic field lines as well, because they all have to point toward the south. We know the polarity of this because we know these field lines have to be opposing or repelling the other field lines. So simply by drawing the shape and labeling the direction of one simple magnetic field line, then we're able to determine the polarity of this magnets. Okay, let's draw one more. What do you know about this beyond what I've already given you here, that one end is north? Yep. Okay, good. The other end is south. What else do you know about it? Yeah, Roger? The north end is being held near a south end, so this end right here? Good. And how do you know that, Roger? Good. The field lines are connected. That means it's an attractive force. And that's one of the laws of magnetism as well, right? First one was like poles repel each other. Second one, unlike poles attract each other. Since this field diagram is showing attraction, then we know that the field lines are since the field lines are joining to each other, then we know it's showing attraction. We know they have to be opposite poles there. One other thing we know is this got to be north, obviously, right? Okay, got to be north. Can't have just a south magnet. You got to have a north-south magnet. Finally, we do know the direction of this as well, right? Which way does this field line point? Right here. From left to right or from right to left? Yeah, it's going to point from left to right. And of course, the rest of them are going to point from north to south as well. Does that make sense? When field lines join each other, when field lines leave one magnet and go to the next magnet, it means it's going from a north pole to a south pole. When field lines leave one end and they repel the field lines from another end of another magnet, then that means one end is north and the other end is north, or one is south and the other is south. They've got to be like poles. Does that make sense? Most times we see at the unit test or a diploma exam, we will see a question on field lines. Okay, we will. Just like on your unit test for electricity, you saw that electric field diagram, right? That first question. Okay, pretty straightforward question, right? Okay, I think all of us, or pretty much all of us, nailed that question. We're likely to see something like that again. A little bit more confusing for magnetic fields because it's the equivalent of having 4 charges instead of 2 charges, right? Okay, but if we remember the basic rule, That is, field lines go away from north toward the south, and when they join up, it means you have opposite poles. When they repel each other, they have like poles. Okay, then we should be able to do this. Even if you get a scenario that looks a little bit different. Okay, maybe you get 3 magnets or something like that. It's not likely, but okay, doesn't really matter. Okay, you can still determine what the polarity is based on whether field lines are joining each other or not, and what the direction of those field lines are. All right. That's pretty much where we left off yesterday. I got a little chart for you. You don't need to write this down. It's not something that you need to know in terms of remembering numbers here. But I just want to draw your attention to some of the relative strengths of a magnetic field, just to give you perspective. By the way, the symbol for magnetic field is a B. It's a vector field, so it has that little arrow over it. It has a direction associated with it, of course, just like gravitational field and electric field. The unit for magnetic field is T. It's a Tesla. Now, the Earth's magnetic field, that's the one that we're exposed to most often, right? Every day, all the time. The Earth's magnetic field, I told you, is very weak. It's about 10 to the minus 5 Tesla. Now, it varies. It varies depending upon where you are on the Earth. The magnetic field here might be different than the magnetic field at the North Pole or at the South Pole or in Toronto or wherever. The magnetic field varies depending upon where you are on Earth. But on average, the Earth's magnetic field is about 10 to the minus 5 Tesla. It is, however, decreasing. It's decreased in strength dramatically in the last couple hundred years, like dramatically by double-digit %, okay, which is leading some scientists to believe that it's actually in the process of reversing. We don't know that, but we do know from geological records that the Earth's magnetic field does reverse, and it happens on average about every 250,000 years. And we do know that it's been 750,000 years since it's happened the last time. So usually it's every 250,000 years. We're about 500,000 years overdue, and the Earth's magnetic field is decreasing dramatically over the last 100 or so years. So maybe it's in the process of reversing. We don't know. Okay, nobody really knows. If it does reverse, it's not going to happen tomorrow. It's not going to happen overnight. But it also might not necessarily be a 1,000-year process. It could be a 50-year process. It could potentially happen within your lifetime. Okay, we don't know. Okay, it's one of those things that it's kind of conjecture almost or theoretical until it actually happens. Yep. How would that change things? Well, it could have a number of implications actually. If it reverses, and in that process of reversing, decreases to 0, and then increases as it goes the other way. While at 0, that presents some problems for us. The Earth's magnetic field provides us with a shield from charged particles coming from the sun, solar wind particles. Okay. And you'll see why it shields us later on in the unit as we look at the interaction between electricity and magnetism. Well, that shield's not there. Okay. That shield's not there if the Earth's magnetic field becomes 0 for a brief time. Now, the Earth's atmosphere will also protect the Earth from these charged particles. So it's not like we're completely, unprotected, but we would have less protection, and there would be increased incidences of cancers and things like that as a result of that. But we're not talking necessarily something catastrophic, not the end of the world kind of thing, but it would have navigation implications because, of course, navigation, not so much now as it would have, say, even 10, 20 years ago, but because now everybody uses GPS, right, which isn't based on magnetism. Hey, but if you're lost in the woods and you're using a compass is going to point the other way if the Earth's magnetic field is reversed, right? Biologically even, I'm not sure, to be honest, what kind of implications it would have for things like birds, because how do you think birds get to fly south? How do you think birds fly south in the winter? They've got this tiny little compass, this tiny little magnet, effectively, in them that kind of guides them in the right direction. So I'm not sure what kind of implications it would have for that. Yep. I don't know records. All I know is what I've read their records. So let's take a look at another one here. Again, you don't need to write these down. I just want you to kind of have perspective as to orders of magnitudes. A bar magnet, hey, the bar magnets that you guys used yesterday were pretty weak. I actually strengthened those magnets yesterday after class. Much, much stronger now than they were yesterday. But even yesterday, they were much stronger than the Earth's magnetic field. You might not think so. You might not think so because, man, you bring them together, they hardly attracted each other at all. But when you brought the compass nearby the bar magnet, what affected that compass more? The bar magnet or the Earth? The bar magnet, right? So the bar magnet's magnetic field was stronger than the Earth's magnetic field by a lot. On average, a bar magnet is about 1,000 times stronger than the Earth's magnetic field, 10 to the 3 times stronger than the Earth's magnetic field. A sunspot, this weather kind of that's taken place on the sun, releases these charged particles, produces a magnetic field that's about 10 times stronger than that. Okay, about 10,000 times stronger than the Earth's magnetic field. An MRI, who's ever had an MRI for something? Yes? I had an MRI on my knee once. I hated it. It was, and because it was on my knee, it was about the easiest MRI that you could possibly get, right? Because the lower half of your body is inside this, you know, sometimes you see those storm drains, those drains like that, you know, that come out of storm drains and enter into the river or whatever, and they're about this big, okay, big around, like this tube, and an MRI machine feels like you're inside one of those. It's like if you're claustrophobic at all, it's bad. But only the lower half of my body was inside it. If you get an MRI somewhere else on your body, then your entire body has to be in it. And they tell you before you go in there, you can't move. Like you can't budge. And you're in there for like 25 minutes, which it would be better if they didn't tell you you couldn't budge, because then you start thinking about it, and then it's really difficult to not move at all when you're in there for 25 minutes. Anyways, when you get into, before you have an MRI, they give you this survey and ask you a whole ton of questions like, you ever had metal in your eyes? Like, really? Why would they ask you if you ever had metal in your eyes? Yeah, like all kinds of questions like that. What does it matter? Well, for some types of metal, it doesn't matter. If you've ever had copper in your eyes, well, it might matter, but it doesn't matter for purposes of an MRI. If you've ever had steel in your eyes, then that might be a problem getting an MRI. Why? Because it's a pretty strong magnetic field, right? It's 10 to the 1 Tesla. It's 1,000 times stronger than a bar magnet. It's 10 to the 1 Tesla. Maybe it rips the steel out of your eyes. That wouldn't feel very good. I know, I'm not sure, to be honest, I'm not sure how much of an effect that would have, but clearly they're thinking about it as they ask you those questions. I know my father, when he worked, he's retired now, but when he worked his whole work as a heavy equipment mechanic for a construction company, and he's about the toughest man that ever. He would come home from work some days, and the things that happened to him at work, I think like unbelievable. Some of the things that would happen to him. Like one day, I remember he came home, and this hurt. Like this hurt him. And if it hurts him, it's a lot. He came home with this chunk of steel stuck in his arm, right in here, this big bump, and it's all red, it's bloody, like, you know, whatever. And anyways, he had gone, they actually took him to the hospital, and they said, basically, you know what, we're better off leaving it there. We're just leaving it there. So now, to this day, you look at his arm, and there's this big bump on his arm, because there's still a chunk of steel in his arm from grinding something in the shop at this construction company. He went to get an eye test here a couple years ago, and the eye doctor said, I think you've got something in your eye. So the eye doctor looks at it closer, and it's these shards of metal stuck in his eye. Didn't even feel it. Been there for years, just from, whatever he did one day at work. Anyways, he said an MRI. I don't know how they dealt with that. I don't know how they dealt with these shards of steel that were in his eye. I guess when he answered the questions, the little survey, he didn't know that he had these shards of steel in his eye, so just said no. Apparently didn't hurt it. Okay, but it's risky, right? Because the strength of this magnetic field, pretty strong. 15 Tesla is a strong magnetic field when you compare it to a bar magnet or especially the Earth's magnetic field. Hey, the strongest human-made magnet, 40 Tesla. It's only about twice as strong as an MRI machine. So like an MRI machine is pretty strong when the strongest one ever made by humans is same order of magnitude. This is the guy you want to stay away from, this magnetic neutron star, because it's 10 to the 11 Tesla. This is the kind of thing that if you could get close, which you couldn't, but if you could get close, then it's probably a strong enough magnetic field to suck the iron right out of your blood and suffocate you because you don't have any iron in your blood and you don't have the oxygen going to your brain. The good news is, hey, don't need to worry about that. The good news is you'd be dead long before you ever reached the magnetic neutron star if you were trying to travel there. Okay, so again, don't memorize these numbers. I don't care if you know these numbers, but I do want you to know that, hey, look, the Earth's magnetic field is pretty weak, right? Compared to a bar magnet, compared to the strongest human-made magnetic field ever found. Hey, you see a chart like this, you don't memorize the numbers, but sometime down the road, 3 months from now, you're doing a question, you're solving for a magnetic field of an MRI machine, and you get 6,000 Tesla. Well, you're wrong. Right? You don't need to remember that it's 40 Tesla, but you know that 6,000 is way too big, right? If you remember orders of magnitude, that'd be great. But even if you just kind of remember, like, basically, this one's a lot stronger than that, then that's probably okay. Yep. When you drop an aluminum bar, yeah, through the magnetic field. We're going to show you that demonstration actually later on this unit, like literally at the very end of this unit. Not with the aluminum bar, but something pretty similar to that actually. Okay. That's not a strength of a magnetic field though thing. That's these eddy currents as you're saying. Yeah, no, that's right. The stronger the magnetic field, the more magnified that's going to be. Yes. Yeah, for sure. Okay, I do want you to copy down this. This is a comparison of the three fields that we've done to this point. Gravitational field, which we focused on this year earlier as we were talking about electric fields, but really we did it last year. Electric fields, which of course is new this year, and magnetic fields. The source of a gravitational field, of course, is something with mass, something heavy. You produce a gravitational field, albeit not a very big one. The Earth produces a really big one because it's heavy. An electric field, the source of an electric field is a charged object, positive or negative charge. So you got one kind of producer for a gravitational field. You got two kinds of producers for electric fields, positive or negative. In a magnetic field, before you get too crazy in writing this down, the source of a magnetic field, sometimes in physics we just want to sound smart. What's the source of a magnetic field? A ferromagnetic material with aligned domains. What's an easier way to say that? A magnet. So if you want to just write down a magnet there, that would probably be okay, because that's the same thing. The direction of a gravitational field is always toward the producer, and it can be attractive and just attractive for gravity. An electric field is away from the positive toward the negative, or you could think of it as the way that a positive particle moves when placed in the field. It can be attractive or repulsive. And finally, a magnetic field can also be attractive or repulsive, but it's from north to south, or the direction that a compass needle points when placed in the field. So this table has nothing new. You've learned it all before. It's just a nice little summary of these three fields that we've seen to this point. What I'm about to show you now is going to change your life. It's going to change everything you've ever believed in. You have a picture of the Earth here. The Earth doesn't have a magnet inside it, but it's like the Earth has a magnet inside it because the Earth's magnetic field shape and direction looks very, very much like the magnetic field surrounding a bar magnet. Okay, we got a bar magnet right here inside the Earth. We got magnetic field lines pointing, going in this shape, so on and so on and so on. Now, hold on, Rutger. We put a compass in that magnetic field. Which way does it point? Well, we put a compass in the magnetic field that points this way, right? Points towards northern Canada. Well, then that's the direction of the magnetic field. But we also defined magnetic field as being from north to south. So this has to be the North Pole, this has to be the South Pole. That means that what we typically think of as being North Pole and South Pole magnetically isn't correct. Geographically, the North Pole is northern Canada or close to Canada. But magnetically, that's not correct. Magnetically, northern Canada or close to northern Canada is the magnetic South Pole. So what I'm about to tell you is this. The penguins that live down there in Antarctica don't live in the South Pole at all. We always say, where do the penguins live? They live in the South Pole. No, they don't. The penguins live in the North Pole. And finally, this is why, when you were little and you went looking for Santa Claus, this is why you couldn't find him. Because you're looking in the wrong place. Santa Claus doesn't live in the North Pole. Santa Claus lives in the South Pole. Now, magnetically, guys, magnetically, this is absolutely true, right? Magnetically, northern Canada or close to northern Canada is the South Pole. Now, that doesn't change the way we navigate, right? Navigationally, we still call it the North Pole, but it's not the North Pole. We just call it the North Pole. We could call it whatever we want. We could call it X. As long as everybody is going by the same frame of reference, it doesn't really matter, right? If I was to send Jazzy to the office for being late, I wouldn't do that because he's never going to be late again. But if I was to send Jazzy to the office for being late, I said, Jazzy, go to Mrs. Stafford's office. I'm tired of you being late. And Jazzy thought Mrs. Stafford's office was down that way at the end of the hallway. But Mrs. Stafford, which is not there, right? Yeah. It's not down there. But if Jazzy thought it was down there, then he might go to the wrong place, unless Mrs. Staffordchuk, for whatever reason, also thought her office was down there, and everybody else in the school thought her office was down there, and her real office was sitting empty up there. It doesn't really matter if Jazzy knows where her office is, as long as everybody in the school, including her, is going to the same place. As long as everybody is assuming her office is there, then Jazzy goes to the right place, goes to see her, right? So as long as everybody is working on the same frame of reference, it doesn't matter that we call this the North Pole up here, but that it's really the South Pole. When you're lost in the woods and you look in your compass and you're navigating, hey, you're looking north, or your compass points north, right? But it doesn't really point north. It really points south. But everybody says it points north, so that's okay, because we're all on the same frame of reference. Now, magnetically, it's south. Geographically, it's still north, but magnetically, it's south. Riker? No, that's right. Yes, yes, I do. If you're close enough to the poles, the compasses don't work. And Rutger's asking me if I know why, and yes, I do know why. Does anybody else know why compasses wouldn't work when you're close to the poles? Yeah. 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 In the end, when you're up here in the magnetic South Pole, which we think of as the North Pole, because that's where Santa Claus lives, right? the compass needle wants to point down, right? I'm right above it. The compass needle wants to point down. Look at the magnetic field direction. It's pointing down. The compass needle can't point down because it's a horizontal axis. The only way that you can make that work is if you had like a 3D compass, which does exist. You can have a needle that's kind of allowed to rotate on the X and the Y axis and the Z axis. So like a 3D compass, which actually could point down. Sorry. Yeah. That make sense? Ricky, you just asked a question that's going to be asked in one of your check and reflect questions later on. Now everybody knows the answer to it, right? Everybody at least better know the answer to that question.